So I think from example that we already talked, okay, we already talked in this in in this video. So you can see that if we have a basis that orthogonal, or we have orthogonal basis, so you can find the complement of orthogonal. I mean, you can find the complement of vector that orthogonal to the subspace easier, and you can find the coordinate vector easy, right? So our question is, so if we have a vector space, okay, so we know that if we have a vector space V, so we can so we have a basis, but this basis maybe it's not uh maybe it's not orthogonal. So our question is, can we change this basis, or the basis F to be orthogonal basis? Can we change it? So if can be changed, how? Okay. Before we are talking about the process, so I will I will need you some motivation. Okay. Okay. First we start with R2. Okay. So if we have two vectors, okay, so I have the vector u and v here. Okay. So you can see that the vector u and vector v are not perpendicular. I mean, they are not orthogonal, right? So how to find the orthogonal basis by using vector u and v? Okay, so the first one is we will use the base. I mean, we choose the base for the vector. Okay, so first I choose this one. I choose v as the base. Okay, and from this one, so I focus on the vector u. Okay, so we know that if we have vector u here, you can find the projection, right? The projection of u on v, right? And if we can find the position of u on v, so we can find the component vector of u that orthogonal to the vector v, right? This one is v minus projection of u on v. Okay, so we have two vector here. Okay, what does it mean? It means that we can choose, and you know that the R2 it has the dimension equal to 2, right? What does it mean? It means that if we have two vector that that linearly independent, so it's okay to be a new base. So from this one, we will use a new base like this. The first is we obtain from v, and the next one is this vector is the v minus projection of u on v, right? This one is the new basis for R2, and you can see that the two the blue one and the green one are orthogonal, right? Okay, this one is from R2. Okay. Next, now we focus on R3. Okay, and we know that the R3 has the dimension equal to 3. Okay, so we have this three vectors here: a red one, blue one, and green one. It's hard. It's quite hard to draw it. Okay, So it look like so you can look it as a three a three-dimensional shape. Okay. Okay. How to find the orthogonal basis from this one. Okay. Also, we let the red one is u, the blue is v, and the blue one is w. So how how to do this? Okay. So the first one, we need to focus on the two vector. Okay, so I focus on vector u and v, and we start with the vector u. What does it mean? It means that we use u as the base. Okay, and then for the vector v, because because we know that if we have a two vectors, you can find you can find the component of that vector that orthogonal to another vector. Okay, so what does it mean? It means if we have a vector u here, okay, so we find the the complement of vector v that orthogonal to vector u. So we use violet here, bob. Okay, this one. So how to find it? So the first one, you need to find the projection, right? You need to find the projection of the u of the v on u. Okay, and we obtain the component of v orthogonal to u is the v minus projection of v on u, right? Okay, and for this one, we will not use v, right? Why we not use v? Because we use this vector. I mean, we use the v minus position of v, v minus position of v on vector u to be the basis that span by two vector, that's span by u and v. Okay, and next, what about the view? Now the view is like here, right? And we know that from this one, if you need to find the vector that that perpendicular or that orthogonal with two vector here, the vector u and the v minus position of v on u, so you need to project this one, right? You need to project the view on the plane, right? On the plane that span by vector u and the vector and this vector v minus position of v on u, right? So how to project it? So the project is this one, right? Is the v projection of v u. Okay, and we project it. Okay, we obtain the vector blue one and obtain a brown one here. Okay, and for the blue one, what is blue one? Blue one is the projection of the green vector. The green vector is the blue, right? So the blue one is the projection of the blue on the space that span by two vector, or the space that span by two vector, right? But the span of the two vectors, I mean the span of the vector u and v, now is equal to the span of u and v minus projection of v on u, right? Okay, and we denote this set is w. Okay, so the projection of the vector w on the view, this one, right? And what is the brown one? So the brown one we obtain from W multiply W minus with the projection of the vector W on uh, on plane W. Okay, and from this one you can see that we obtain three, right? We obtain three vectors that orthogonal, right? So this is how to change or how to obtain the basis. Okay, how to obtain the orthogonal basis from the basis. Okay, so you can see that if we have if we focus on R4, so we need to do this process, right? So we choose the first vector, and when you choose the first vector, so we find the orthogonal of the second vector, and you find the projection, and you find the orthogonal projection, and you do it again and again. Okay, so from this one, so you can see that it's like the algorithm, right? So, and this algorithm, we call this algorithm is the Gram-Schmidt process. Okay, so the Gram-Schmidt process is the process that to convert the basis U1 to be an orthogonal basis V1 to be R. Okay, by using this formula. Okay, so number one, so by following this step, so we obtain that V1 is, so we set V1 equal to U1, right? And V2, we set is equal to U2 minus this vector. So what is this vector? Actually, this vector is, what is this one? Yeah, this one is the projection of V1 on U1, right? Oh, sorry. This one is the projection of the U2 on V1. Okay, and what about this? Actually, it's minus of this vector, right? So what about this one? This one is the projection of U3 on the span set of V1 and V2. Okay, and you do it again and again and again. Okay, and the process must stop because we have R element. Okay, you do this process. Okay, and this process we call the Gram-Schmidt process. What does it mean? It means that if we have a basis, so you can change the basis to orthogonal basis. So that's why we can conclude that if every vector space has orthogonal basis. Okay, so if we need to if we need an orthogonal basis, you can do it also by using the Gram-Schmidt process, and you normalize. Okay, and you normalize each vector. Okay, so that's why we lead to this. Oh, actually we have a proof, but for the proof is we use mathematical induction to show that if it has one vector, two vector, three vector, and we have a k vector, so this formula hold. Okay, so this is how to prove it. Okay, so we consider only one vector, and we consider the k vector, and we will add and we consider the vector uk plus 1. Okay, and we will show that the span of the u1 to uk plus 1 is equal to the span of v1 to vk plus 1. Okay, so if you need to read the proof, or you need to copy this page, so please pause it. Okay, we have second part here. Okay, you need to understand the proof by yourself. Okay, So this is our theorem. Okay, so that I told you before. Every non-zero finite dimensional inner product space has an orthogonal basis. Okay, and the proof is very easy. Okay, the proof is three lines นะครับ okay, we let V to be a finite dimensional inner product space, and then we already know that every vector space has a basis. Okay, and we use the Graph-Schmidt process to convert B to an orthonormal basis B prime. That's all. Okay, so we will move to the next example. So how to use the Graph-Schmidt. Okay, we assume that R3 has the Euclidean inner product. Okay, and we apply the Graph-Schmidt process to transform the set of U1, U2, and U3 to be into an orthogonal basis, and we normalize it to obtain the orthogonal basis. Oh, this one is not hard, right? We use the Graph-Schmidt process here. Okay, so how? Okay, first we let V1 is equal to U1 here. Okay, and next V2 is equal to U2, and minus the inner product of U2 and V1 over V1 inner product of V1 and V1. Also, this one actually the inner product of V1 and V1 is the norm square, right? It's the norm of V1 square. Okay, and multiply with V1, and for this one, so we calculate this one. This one is equal to 203. Okay, and next for the V3 we apply the Graph-Schmidt process again, and we obtain this vector. Okay, so for the calculation, so I will skip calculation. Okay, we will use, so I need you to know about the how to use Graph-Schmidt process. Okay, so now we obtain that V1, V2, and V3 is an orthogonal basis for R3. And next, we need to find the orthogonal basis, right? So we will find the norm of the V1, V2, and the norm of V3, and we can show that Q1 is the V1 over the norm of V1, and we obtain the vector like this. Q2 is this vector, and Q3 is this vector. So it's not hard. Okay, it's not hard to do that. Okay, if you need to copy this page, so please pause it. Okay, I think this example is quite easy because we apply the Graph-Schmidt process in the set of Rn, right? But we know that the Graph-Schmidt process can be applied for every inner product space, right? So what does it mean? It means that if we have the vector space with the inner product, and you know the basis for that inner product space, so you can find the orthogonal basis by using the Graph-Schmidt process. Okay, that's why we move to the next example. The next example is P2. Okay, everyone know P2, right? P2 is the set of all polynomials that degree less than or equal to 2, right? And we know that the standard basis for 1x and x squared, I mean the standard basis of P2 is 1x and x squared. Okay, and I need you to apply the Graph-Schmidt process to transform this set to be orthogonal basis. Okay, so it's not hard, right? Because we know the Graph-Schmidt process formula, so we apply that formula. But one thing that you need to beware is the dot product or the inner product that we use this inner product. Okay, what does it mean? It means that by Graph-Schmidt process we choose phi 1 equal to 1, right? And phi 2 is we choose x and minus with the inner product of the phi 1 and x over phi 1 inner product of phi 1 and phi 1. And so we need to find the inner product of phi 1 and x. So what does it mean? It means that the inner product of phi 1 and x is equal to the integral of 1 times x dx over minus 1 to 1. And this one is equal to x squared over 2. And we evaluate from minus 1 to 1. And this one is equal to 0. So that's why phi 2 is equal to x. Okay, for phi 3, we apply the Schmidt process. Okay, we use the x squared minus the inner product of phi 1 and x squared, and phi 1 over the inner product of phi 1 and phi 1 times with phi 1 and minus the inner product of phi 2 and x squared over the inner product of phi 2 and phi 2 times phi 2 here. Okay, and from this one, we calculate the integral of 1 and 1 multiplied with x squared, right? The inner product of the phi 1 and x squared is equal to this one, and this one is equal to 2 over 3. Okay, so calculus required. Okay, so for the inner product of phi 1 and phi 1 is the integral of 1 multiplied by 1 dx over from the minus 1 to 1, and this one is equal to x evaluate at minus 1 to 1, and this one is equal to 2, right? And the last one, the inner product of phi 2 and x squared is the integral of the x cube, and we evaluate from minus 1 to 1, and the formula for the integral of the x cube is x to the power 4 over 4. Evaluate from minus 1 to 1, and this one equal to 0. Okay, so that's why we obtain that phi 3 is equal to x squared minus 1 over 3. Okay, so by Schmidt we obtain that this set is an orthonormal basis for P2. Okay. From this example, so this example, so we can find an orthogonal basis for P2. So I have some homework, or some work to do, some work to you. Okay, so fine. So my work is my task is find an orthogonal orthonormal basis for P2 by normalize. Okay. By normalize the basis from the previous example. Okay, please do this question. Okay, and if you do this question, so present this question or this assignment, or present your solution to my chat box. Okay, so if you don't send it means that you didn't see my video. Okay, and next, okay, we will talking about the theorem of the basis. So we know that if we have a basis, if you have a set S, that S is linearly dependent, so we can enlarge that set to be a basis for the vector space, right? So for the orthogonal set, we have something that's like I said before. Okay, So this one is the, if we have a vector, if we have W to be the finite dimensional inner product space, then number one, for every orthogonal set of non-zero vectors in W can be enlarged to an orthogonal basis for W. Okay, and for number two is changed from orthogonal to orthonormal. Okay, so how to prove it? The proof is very easy. It's not hard. Okay, why? Because we will use the extension. I mean, we will use the extension for, extension for the basis, in the basis version that we already learned in chapter 2. Okay, so for number one, if we let S to be an orthogonal basis for non-zero vectors in W, so it means that S is linearly dependent, and then S can be extended to the basis S prime for W. And we use the Gram-Schmidt process to change S prime to be an orthogonal basis S double prime. Okay, so you don't need to normalize them. Okay, and for number two is like number one, but you add the you add the process that you add the normalized each vector in S prime. Okay, so if you need to copy this space, so please pause it. Okay, we move to the last example. Okay, so if we let a vector u1 and u2 in R3 like this, u1 is 1 1 0 and u2 is 1 minus 1 2, so find an orthonormal basis for R3. Okay, how to find it? From this one, the first one, you can see that the vector u1 and u2 are orthogonal. Why u1 and u2 are orthogonal? Because okay, so this example, they didn't give us about, they don't give the inner product to us, so we will use the Euclidean inner product. Okay, so why u1 and u2 are orthogonal? Because the inner product of u1 and u2 is the 1 times 1 plus 1 times minus 1 plus 0 times 2, and this one is equal to 1 minus 1 plus 0 and equal to 0. So u1 and u2 are orthogonal, right? And now we will find the vector u3. Okay, we will find the vector u3 that u1, u2, and u3 are the basis. And it's not only basis, it is an orthonormal basis. So we will apply the Gram-Schmidt process. Okay, we apply the Gram-Schmidt process for this one. So how to find this? Okay, before we find this, so we need to enlarge. Okay, we need to enlarge the set of u1 and u2 to be the basis for R3. And next, we will use the Gram-Schmidt process to change that basis to be an orthogonal basis, and we normalize again to obtain orthonormal basis. Okay, so this is our solution. Okay, so first we enlarge. Okay, we will enlarge this set. So I call this set is an S. Okay, and we consider that this set u1, u2, and u3, where u3 is equal to 1 2 and 1 2 0. Why I use this one? Actually the vector u3 maybe it's not equal to 1 2 and 0, so you can use any vector, but you need to make sure that this vector, but you need to make sure that u1, u2, and u3 are linearly independent. Okay, and why you need to make sure that u1, u2, and u3 are linearly independent? Because if you know that the set S is linearly independent, and then we can conclude that the set S is a basis for R3. Okay, and we can show that if we choose the u3 is the 1, 2, and 0, it's easy to see that u1 is not scalar multiple of the u3, and u2 cannot write as the linear combination of u1 and u3, right? Yeah. So the set S is linearly independent, and we obtain that S is a basis for R3. Okay, and then next we use the Gram-Schmidt process to obtain the basis, to obtain an orthogonal basis. Okay, by we let V1 to be U1 here, and V2 to be U2 minus V1 inner product of V1 and U2 over the inner product of V1 and V1 multiplied by V1, and we obtain the vector 1 minus 1 and 2. If so, this vector is like look like vector U2, right? Okay, and for V3 we apply the Gram-Schmidt process to obtain this vector, the minus 1 over 3, 1 over 3, and 1 over 3. And for the detail of calculation, I already add it in the bracket. Okay, so we obtain an orthogonal basis for R3, and next we need to find the orthonormal basis for R3. So that's why we find the norm of V1, V2, and V3, and we can show that the norm of V1 is square root 2, the norm of V2 is square root 6, and the norm of V3 is the 1 over square root 3. Okay, so we normalize it. Okay, and we can show that this set is an orthonormal basis for R3. That's it. Okay, it's done. Okay, if you need to copy this page, so please pause it. Okay, before we end this video, so in this question, so you know that this one is the vector on in R3, right? And you know that, and you know the operation in R3, that you know that if you have a vector u and the vector v, you can find the u cross v, right? And what is the u cross v? The u cross v is the vector that obtained by the right hand rule, like this, right? If you have a vector u, if you have a vector v, the vector u cross v is this vector. Okay, and the property of the u cross v is u and v are orthogonal with u cross v. Okay, what does it mean? It means that inner product of u and u cross v and the inner product of v and u cross v is equal to 0. So from this question, if you let u3 to be u1 times u2, and when you normalize it, and you normalize it, and if you normalize it, you will obtain the orthonormal basis also. Okay, but actually in my assignment, I have equations, or I need you to prove that if we have a vector u and v, where u and v is linearly independent, on R3, so we can show that if we let W is the span of the vector u and v, then W perp is the span of the vector u cross v. Okay, this is the questions for my assignment. Okay, so I think so you need to do this. Okay, so this is the last video for this semester. Okay, good luck.